Welcome to Academic Daddy's tutorial. In today's class, I'll be teaching you chapter 9, that is elasticity and friction. So under elasticity, I've sectioned it under, under areas of key concentrations. There you have it. So elasticity, Hooke's log, Robert Hooke's graph, modulus, types of modulus, energy stored in an elastic string, the different cases, energy stored in a wire. So that's the section I'll be treating. So in my next video, I'll be treating section 2, which is all about friction. Then the textbook exercises and conceptual case questions with the answers. All right, let's get to it. First, what is elasticity? So the way I want you to understand this elasticity is simply if it regains shape after force is removed, it is elastic. If it doesn't regain, it is plastic. So we simply say that elasticity is the measure of solids or anything's ability. So let me use solid, of solids ability to regain shape or volume when deforming force is removed. If this looks like too much English for you, the way I want you to speak your own is simply elasticity is simply going back to the shape after applied force is removed. While not going back to the shape after applied force is removed is what we know as plasticity, or you see plastic. So if you know that Robert Hooke's, I always remember the year because it involves 16, and I was born on 16th February. So 16th, then you just add 97 there for me. So Robert Hooke's in 1697. I know there are people that proposed this thing before him, but it's just that he was the one favored or that had much to make it his own idea. Because that's how I've discovered everything about all these concepts. There are people that even mentioned or did something on that, but one person will come and take the whole glory. So they said that Robert Hooke in 1697 worked on a graph, like he stretched objects, and he came up with this concept, this graph you normally see. And he said that in this, that whenever force, sometimes you see it as force, and you know that force is mg, so sometimes you can also see it as m against extension, or you see it force against L. And you know that whenever you have, so the slope of this Robert Hooke's this thing is force over length, and force over length is the same thing as surface tension. While the area, we know that area is simply the vertical axis multiplied by the horizontal axis. That is why it's meters square. So if I know that I'm having F on the vertical axis and X, which has L as its dimension. So when you have force and length multiplied, is the same thing as work. So the area of this Robert Hooke's idea is work done. So he said that whenever you stretch a body, that provided the elastic limit is not extended, that the applied force is directly proportional to the extension, or you see the load. And I want you to understand, like as I'm saying this, I'll be remembering some things. Whenever you see maximum load in the course of this physics or in physics, the first thing I want you to think of whenever you see maximum load, some people think it's kg. No, the first thing I want you to think of is force. Then if it's not force, they're talking about pressure before you now start looking at mass. For in engineering, key concepts like these are used whenever you deal with constructions and all that. So if you know this now, so I've noted this. So the concept is that if you stretch a body, that let's say this is A, that if this body gets to this place and you remove your hand, it will come back. But let's say this point is B, that if you exceed this place, so we call this place proportionality. limits. So they are equal. You stretch or notch, then you stretch, it comes back. But here, once you reach this point, this B, it starts showing you sign. The minute you remove your hand, it can come back. But the minute you exceed it, that what happens is that this thing will no longer go back. So this now, let's say I call this Y. This is what we call the yield point. So as you go on, sorry, so at this yield point, it can now, you can now see that it is no longer going to come back. So you now have this. So you can see that at this point now, let's say I call this J. So at this point you have the breaking point. So what this is law is trying to say is, in essence, that whenever you have this, you can clearly see that provided elastic limits. So talking about Hooke's law now, Hooke's law is simply focused on this extent. So that's just what Hooke's law is all about, just this extent. So you can see that if you check this area under this graph, you can see that it's simply F and X. And notice something. This thing that you have here is the same thing as saying I have a triangle this way and I have a triangle this way. And area under a triangle is simply half base times height. And the base here is X, the height here is F. So that is why we simply say that the work done or the area under that Hooke's law is simply given by half F X. So from this triangle, there are sometimes you see things like work done. You see something like this in your textbook. Let me do it with you here. They say change in the work done is directly proportional to the force applied at a particular distance, at a small distance. And whenever you say small distance or small anything in physics, it means change in that particular area. If I say small work, it means change in work. If I say small pressure, it means change in pressure. So if I know this, then I say if you want to make work subject of formula, if you cross this over, you now see that this is going to be integral of f dx. But there's this general belief from this same Hooke's law that if you state his law, he says the force applied is directly proportional to the extension. You get the English? So that means that if you now make F equals to Kx, this is proportionality constant. That means that F naturally, force on its own, is directly proportional to X. So let me replace it here. You always have to replace it. So if I know this becomes Kx dx. And dx means with respect to x once you are putting integral. This d crossed over to become integral, changing. So that distance will change. So this becomes w work equals to. So bring out k, since it's a constant, integrate x with respect to x. And integration simply means you add, once I'm integrating, I remove that sign. You add 1 to the power. There's an invisible 1 here. 1 plus 1 is 2. Divide by the new power. So, and you know I did this to the x because of this with respect to x. This thing is telling me it's s, I do it to. So if you look at this now, you now see that this is now w equals to, this is over x, which is the same thing as saying half kx square. So work is equals to half kx square. So if I know this, we can see that this is also this thing now that we have here. If I don't want to use this triangle, or this graph of Hooke's to discover work done, still talk about work done proper, I can just use this integration. So if you check it, since we said that force is equals to kx, I can come here and replace. And remember, please remember something. Yes, this is going to be kx, and there's x here already, x. Then I bring the half. So if you put it where, you now see that this is half kx square. Work done. And this is also the same thing as energy. because work done is the same thing as energy. So I want you to always understand that whenever we are talking about this kind of work done, it's talking about a spring or a strength. When it gets to wire or anything that has volume, I'll show you another method of doing it still from this concept. So now that I know this, let's go back to what we are doing. So what led us to this is that we cannot talk about Hooke's law without talking about what his graph was all about. So remember it's in 1697. So let's go to the next part. So the next part, okay, or yes, okay, yes. So I just feel like we cannot just, okay, so let's, yes, let me just focus on finishing everything about work done. So see, let me focus on finishing everything about energy stored in a string or a spring. Then talk about energy stored in a wire before moving to modulus and types of modulus. So I think it's best that way, so that I'll be sure that I'm not doing modulus and now coming back to go to work. So if I know this, I can now say that if that is the case, see, you need to know that work done in stretching a string, work done or energy stored in a string, in a energy, energy. Let me do this thing here. The book is misbehaving. So energy stored in a spring or string. They are the same thing, just that string, when you stretch it, it tends to become plastic more than spring does. Spring is more elastic. So energy stored in a spring or string, whichever one you see, is the same thing. Then, or you say another way to say it is work done by a spring. So any of these that I'm using is still okay. So what is it all about? What work done or energy stored in a spring is talking about is that if, for example, you stretch a catapult, for example, and you allow it, it will return and push that stone you put inside. So what he's saying is that by the time you stretch anything, that thing acquires energy that can do work, and that the work done by a strength is actually the potential energy it acquires when it is stretched. So that time you stretch it, or anything that is strength or even wire, once you stretch it, and you notice that once you stretch it, it tends to increase. That is why you are not seeing anything like minus in that sign. It's not like maybe when you have something inside water, or you come and put something inside water to give it stress, you see that water or gas will leave if it has to do with volume. So work done by a string or energy stored in a string is simply the energy acquired by stretching the string, or you say work done when the string or spring is stretched. So that's how you need to think about it. So if I know this, we say that it is simply, from what I showed you, is simply half fx, or you say half kx square. Don't ask me how I did it. Go back and watch it. You watch, and you get it. So if I know this now, notice that this thing is u for work, and I now have half fx. And notice that that thing, when you stretch it like that, as you stretched it, what it has is the potential to do work. And whenever we are talking about potential to do work, we know it's potential energy. This thing can be mgh equals to half fx, or you say mgh equals to half kx square. So if there's any case where they tell you about heights and tell you that something was stretched through a height, it has mass or whatever, this is the formula to use. Now, if there is a case where what you are doing involves something like you finding speed of what you stretched, you now need to remember that from mechanical energy, from mechanical energy, we always say that mechanical energy is equals to potential energy plus kinetic energy. And I told you when we did dimension that anytime you have this kind of thing, that it means that the dimension is equals to this, and the dimension is also equals to this. So from these three things now, let's say this one is work now. Let's say this is potential energy. So what this thing means is that this can also be the same thing as saying U here now can be equals to, if it's a string, half kx square, which is just as half fx plus half mv square. This can also mean the same thing as saying u is equals to half kx square or half fx. This can also mean the same thing as saying, and since this is this way, this means that potential energy can also be equals to ke. Go back and watch my video, you understand? So this means that u can be equals to half mv square as well, which means this thing now, if this is mgh, that is this one that okay, sorry, yes, if this is this way, this thing now can be the same thing as, if it's ke, since this is potential energy we are talking about, this can be the same thing as saying mgh equals to half mv square, or I can say half kx square equals to half mv square. That is, everything here relates. Depending on how you want to think about it, you know that what physics tends to do is to test your thinking from different angles. Now, this one that is here, potential energy equals to this. This can mean the same thing as saying half kx square is equals to half mv square, depending on what you are given. Even in this place that I did this thing to be this, that is this first one, this thing can mean the same thing as saying mgh, if I have height, equals to half kx square plus half mv square. So this is under the number one. So depending on the question you are given. Also, if maybe what you are dealing with is simple harmonic motion, and you notice that they are talking about the strength and stretching and the energy stored, you now need to remember that from this ME equals to KE plus PE, that mechanical energy for a simple harmonic motion is half KA square. So it will now be equals to half mv square plus half kx square. You say half fx. So depending on what they are asking you to find in that question, any of these formulas can be very correct. And this is when you are dealing with wire. Sorry, this is when you are dealing with string or spring or different cases. Let's say I said this one is the case of simple harmonic motion. So if simple harmonic motion, you have any question related, I will solve question, we'll still get to the question part. So you see the different ways these questions can be asked. So, but it's important you know these formulas and know how it is derived. So, but there can be a situation where they tell you energy stored or work done by a wire. So, work done by a wire, notice is no longer by a string. So, remember, this is work done by a wire we are talking about, and work done is the same thing as energy. So it's the same thing as saying energy stored in a wire. So it's the same thing as energy stored in a wire. The same thing as energy stored in a wire. So I'm being very fast, but I know that somehow you can still understand my handwriting. Energy stored in a wire. So when you hear this, remember I told you that work done by a spring or string is the same thing as saying the work or the energy stored in a spring is simply the work done by stretching it. That is just it. Because you stretched it, it acquires potential energy, the tendency to do work, to shoot out back. So if I know that when it has to do with wire, work done by a wire, or energy stored in a wire, energy stored in a wire is simply work done by stretching it, or you say work done per unit volume. You will say that there's nothing related to wire and volume. Yes, I know. But when you are considering this particular case of a wire, you are considering it in the sense that as you stretch that particular wire, that the area in three places. So see what I mean? If I know, for example, that this is NH equals to half Fx, per unit volume now is simply, remember that this is work done in stretching a spring. Per unit volume is simply everything here. This is work done now, Fx, that is Fs, first times displacement. I've told you that work is first times displacement, not first times distance. The one that is first times distance is moment, and that is why it is a vector. Work is a scalar quantity. So per unit volume is simply, come and put volume here. And the volume we are talking about here is simply, this will be half Fs. The volume we are talking about is simply area. That is area. You know that area is meter square times length. Length is also having the same unit as meter square. So by the time you put it together, you see that you now have meter cube, which is what volume is all about. So you put area, that is, you put length here. So this is simply what you mean by work done by a wire. And if you check it, F over A is simply stress, and another name for stress is pressure, while X over L is simply strain. Extension over length is simply strain. Then you bring your half, that is here. So U is equals to half stress times strain. So whenever you are asked anything that has to do with a wire, the likeliness that if you are finding the energy stored, the formula you are going to be using is simply half stress times strain, because in wire you are considering it to be half work done per unit volume. So it's simply work done per unit volume. And remember that work done by a string is given by half. So in order for you not to forget it, I'll say it's simply half work done per unit volume. So that is the formula to use. So with that said, let's go to the last phase of this particular section or this particular topic. And that last phase is what we call modulus. In mathematics, you must have seen modulus. And your mind is telling you is the same thing as magnitude, that thing you normally do in complex number, where they tell you find the absolute value. No. In this case, we simply say that modulus talks about the extent. Modulus talks about the extent of elasticity or plasticity. It talks about the extent. Modulus is simply the extent of elasticity. You will not see this inside textbook. So you have to take your time and watch this video over and over. Then remember to subscribe. Thank you. The extent of elasticity and plasticity. That is what modulus is. So it's not about every time being young modulus. There are different types. But just know that anything that has to do with modulus talks about the extent of elasticity or plasticity. Or you say the extent of stiffness or no stiffness. Or you just say the extent of stiffness. It's also the same thing as the extent of rigidity or no rigidity. So the extent of anything in physics can easily be said to be modulus. So when you have high stiffness, you say that the modulus is high. When you have less stiffness, you say that that thing is having low modulus, or you say that that thing is actually plastic. So if I have high rigidity, I say that the modulus is high. If I have no rigidity, I say that low rigidity, I say that that thing is having low modulus. So high elasticity, if for example a ruler, I'm trying to check the modulus or the elasticity of a ruler, and the minute I put that ruler, it immediately breaks. It immediately breaks. I'll state that that ruler is very stiff. So because that ruler is very stiff, I say that the modulus is very high. But if I put that ruler takes time. Like, it's not breaking immediately. It's showing me that it has elasticity. that the elasticity is there, I'll say that it has low modulus. So I think the best way to put the elasticity I said is that when it has high modulus, the elasticity tends to be low. And yes, so I think modulus should be going to the side of comparing it with stiffness more. It's more of, or should I say, it's better when you compare it with stiffness. You tend to understand it better. So if something easily breaks or tends to show you that it doesn't have much elasticity, you say that the modulus is high. So this modulus is given by we have different modulus, but I will use E here. So E for modulus, Y young modulus with Y, bulk modulus, which I also call bucket modulus, with B, and shear modulus with G, or you say S. So modulus is given by stress over strain. So if I know this, you remember that stress is force over area and strain is extension over length. So if you do this well, this is where you now see that thing that normally looks like this: force over pi r square divided by x over L. If you remember, sometimes you even see mg for force over pi r square, then divided by, this is the same as times L over x. You might see it as small L, or let me use x. So this is also mg L over pi r square x. So whichever one they are giving you that is valid is okay. So you can even have where they tell you to plot a slope of mass over extension. Then you now have GL over pi r square. Yes. So you can see cases like this. You now have something like slope GL over pi r square. So different ways. It's all about you going through it over and over. You can't understand it. But this is not the case here. The case now is to talk about the types of modulus. So under modulus, we have three major types, and I will talk about those three major types. So the first one is what we call the Young modulus. This Young modulus, we represent it with Y. It is equals to tensile strength, tensile stress over tensile strain. Remember when I told you that if you have force over length, is the same thing as surface tension. So if I know that, anytime you see Young modulus, it's simply talking about tensile tension. It's simply talking about you extending something by pulling it. Maybe you pull it this way downwards and pull it this way. So it requires forces applied at the normal. Normal in the sense that if I apply force normal, it means like more like if I have it up and down or left and right, the edges of that thing, projecting it 90 degrees, maybe horizontally, or 90 degrees vertically, that is perpendicular. So it requires perpendicular forces. So perpendicular forces, whenever perpendicular force is applied, I know that I'm talking about Young modulus, and it involves extending length. So you can see it. But when I have, for example, okay, let me finish the second one. So we have the second type of modulus, which we call the bucket modulus. It's me that call it bucket modulus, so that you know that it has to do with liquid or volume. So, but the main name is bulk modulus. That's the real name, bulk modulus. But I just call it bucket modulus to tell you that it is the modulus of volume. So it talks about the stress ratio to strain when you are dealing with fluids or liquid or things that has to do with volume. So it's no longer, you know that this one here is the sentence as saying force over area all over extension over L, Chevy. But here, this one has to do with force over area all over change in volume over volume. That is why I call it bucket modulus. Volume, whenever you're talking about volume, you are likely relating something to fluids. So if I know this, you now need to check something. If, for example, I come now, and remember that this modulus also deals with perpendicular force. Perpendicular force. So I want you to always think of modulus as you try to apply perpendicular force or parallel force to something. So when I apply perpendicular force, be it in pulling the thing, or I apply tensile. Remember, tensile force. Tensile force is when I am pulling. Tensile force is when I'm pulling. While compressive force, just as name implies, compressive force is when I am pushing. Shebi? Yes, I should be correct. So when I have to push something, it's more like my hand is opening. When I have to push something, it's more like I'm closing my hand. If I have a spread, for example, compressive means I'm pushing my hand together. Pulling means I'm pulling it outside. But once I want you to know under this bucket and Young modulus is that the two of them deals with these two types of forces. So if, for example, I apply tensile force to a liquid having water, you see that definitely the water cannot stay one place, it will want to leave. The same thing with gas. The same thing with if I try to apply compressive force. As I try to compress, that liquid must leave. They don't like staying at a place. So that is why everything that has to do with bulk modulus deals with reduction in volume. So it must carry minus here. So if we simplify this further, we say that bulk modulus B is simply, so please I put this thing for you to note it, is simply pressure minus pressure all over change in volume over volume. Let me do this way. B equals to minus P divided by change in V over V. And this is going to be minus P times V over change in V. And you know that this thing now is the same thing as saying minus PV all over change in V. So you need to note this. You need to note this. From this formula, you can have a lot of things, even when it was here. So here now, this is pressure, P for pressure, and this is formula for pressure. I can also have this thing here, depending on how I want to look at it. There's nothing permanent in physics. So even as you are doing this thing, you can have a case. Remember that viscosity also talks about friction, but in liquids. You can have a case where you bring the two together. But as we progress with questions, you come to understand that one more. So if I have this can be the same thing as saying force over area divided by area is actually, volume is actually area L all over area L. I can have this in a way that this is F E L. Yes, yes, yes. This is change in EL, change in EL, F changing. Let me use D for the change, DAL, and this is AL again. All over, you remember that this thing means everything here is changing V, all over changing, all over V. So that is meter square, L square times L is meter cube. So that is why we use area and length. So all over area L. This is another way you can see this thing, depending, or you see it as mg change in AL all over AL. This thing means changing. Whichever one you see is the same thing. You can also see this thing as mg then pi r square L, that is changing here, all over pi r square L. Whichever one you see it as. So it can, even this thing can be, a lot can be done to this. You can do a lot to this kind of thing. I can even have, assuming I did not change it this way, I can even have this to be the same thing as if F over area, that is B equals to F over area, B equals to, sorry, equals to, then divided by L cube, changing L cube all over L cube. This can be the same thing as saying F L cube, sorry, F L cube all over E L cube. Yes. Okay, A changing L cube. So if you like, get confused, My own is I'm trying to expand, like show you different ways you can use this thing to go on and on. You know, some of you want to get it immediately. You have to take your time. You watch it. Know what madness I'm starting with. So you get it. Now, if I do this, remember that this is MG. Why I'm putting all this is that there are some cases, some books you open, first MG. For some books you open, you start to see different things for that type of modulus. So you don't get confused. Then all over, A here. Then change. Change can be represented with D. Then you have LU cube. This thing you see here can also be written as, let's change the A, then I have pi r square d L cube, D for changing. Now equals to, everything here is equals to B. Everything here is equals to B. So depending on what I want to make subject formula, that is why if you remember that time you do young modulus practical, that time you did young modulus practical, you saw a formula that looks like this. This B can be brought. So we can stop it here, but I just want you to know that this is the main formula. So we just expanded to play with it. There should be no limitation. So the last one is shear modulus. To be honest, this shear modulus, even myself, I understand it, but there's a way I like to understand things that I've not come to understand it, because it's trying, what I don't understand about it is that in the judgment, it looks as if it's just imagination they are using to judge it. Because I wonder how, this is the diagram they normally use. I wonder how you tell me that on a solid body, that you will be able to, let's say this solid body is this way, then you have to push it. Then the pushing you are pushing it now, if this is the solid body, should be parallel. So it's the one that is the only one that deals with parallel force. And parallel force simply means you are not applying the force on it this way or this way, or applying the force on it this way or this way. Rather, you are applying the force this way. So it's more of, it has to do with more of twisting. When you try to twist an object, so it's no longer compressive or tensile force, but the force you get, or sorry, the modulus you get when you do twisting of an object is what we call shear modulus. I understand that one. But what I'm saying is the fact that they are telling me that the object doesn't get deformed. How come? That's rather the object changes shape. If you don't get deformed and you change shape, I understand that you can change shape without getting deformed. But your former shape has been deformed in order for you to acquire that shape. So that's the part that tends to confuse me with regards to this. So I'm still working on it, and I'll still make a video on that when I understand it the way I find it worthy. So this is the diagram you have. They're not telling you that if this was the body, you have this part to be D, and you have a force applied to it parallel. More like when you try to twist, let's say you want to twist, or let's say, I'm looking for a solid to use. Let's say I have an iron, and the way I'm trying to do it is to bend that particular iron. Let's say I'm trying to bend a knife or bend a scissors. The force I apply is not pulling force. If I apply pulling force, it will injure me. The force I have to apply is calmly bending it. Okay, as I'm calmly bending it, you notice that the shape definitely is changing, and to me it feels like you've deformed it from, but just have it in mind that shear modulus is talking about modulus of rigidity. That's another name for it. Modulus of rigidity. Modulus of rigidity. And the agreement by physicists is that shape is what they change. Shape is changed. They say that there is no deformation. That's what they said, which I've not come to terms with. So if you know this, and this is the D, the force applied here is a parallel force, and by the time you do this now, you see that this part tends to change. This part now, initially it was like this. Hmm? Initially. So this is the part you call the S. That is those parts it's left, those areas it's left, and the new area it's created. Those are the parts you call the S. That is the displacement. Yes, now that's what displacement is. Changing of position. The displacement. While this is D. So the angle it goes through in order to get that thing. The angle you have in order for it to get to that displacement is what you call phi. So phi. So this phi now is equals to, let's check. What is opposite? It is opposite. That is S. What is here now? Should be the adjacent. S over adjacent. That is opposite over adjacent. Twa. Twa. Opposite over adjacent. And that means tan phi is what you have to be equals to S over D. So if that be the case, you now go back to what modulus is. So you say that G shear modulus is equals to stress over strain. And the strain here is represented with phi. So all over F over A. So this is the sentence saying F over A all over displacement over the height, or I say the distance. So D, I say S is the displacement of the object. So this shear modulus, I owe you a video on this shear modulus. I will come back to do it when I only understand it the way I love to understand things. Then the D is simply the height of the object. So you can have a case where they give you phi, the angle phi, and the case where they did not give it to you, you just use S over D. That is, this part is the adjacent. Any part, this side is hypotenuse. Now this thing is more like looking like this. So you now have phi D S. This should be the hypotenuse. This should be the opposite of that angle. This should be the adjacent. So thank you for watching this. That's all about elasticity. So I did this by treating elasticity first, then treating work done second, energy stored in wire and the energy stored in a spring. Then you remember I did elasticity on graph second, 1, 2, 3, 4, before moving to modulus 5 and 6. So in the next video I'll be doing everything about friction before we now start looking at the questions. Thank you. Subscribe to my channel.